Just give everybody a minute to get here. Okay, I'm just going to go ahead and start. Welcome to the Breakfast Bash. Good morning, everybody. Today we're going to be talking about tries, which is another tree-like data structure in the same vein as the binary trees that we looked at a couple weeks ago. They are particularly well suited for storing text, and they look like this. And we'll talk about what this means in a minute. So tries are an efficient way to represent sequences of things. So if you have a whole bunch of sequences of, in our case, characters, and you want to store them in a way that it's easy to search and add new things to it and everything, to a data set, a try is a good choice for this type of stuff. So again, in our case, we're looking at characters here. So up until now, we've just been kind of looking at this abstract structure, and I'm not really saying anything about it, but let's pick apart kind of what I mean here. So we're storing a few words in this try, one of which is apple. And each word that you store in a try just is represented by a path in the data structure. So in our case, you just follow some arrows, and when you get to the end, you have a word. I'm just pulling this out here to make it a little bit more clear, but the connections are all the same, but we can just follow A, P, P, L, E, and we have apple stored in the try. If we look back here, if we instead wanted to look up apt is also in the try, but they share the previous two nodes, the A and the P. They just take a separate path down to the T instead of over to the P. And that's really all there is to tries. They're just a tree-like data structure that stores a whole bunch of words. And I guess I should mention that it doesn't have to start with A. In fact, you could have sort of a root node above this that just points to A, B, C, D, E, F, G, etc. And the root node would just have no data in it, but it would provide a way to kind of start your word. So you don't have to just store words that start with A, but for this presentation, I'm just going to work with a try that the root node is A. So it's only going to be words that start with A represented in the tries during this presentation, just for simplicity. So the first thing that we're going to talk about doing with a try is inserting a word. So we're going to insert the word asps into the try. The first thing we need to do is just sort of look at each letter in the word and kind of follow the path that we would expect it to be at down the try. And so we'll do that step by step here. So the first thing is A. Obviously, we have A at the root of our tree. The next thing we're looking for is S, and lo and behold, we have that S right here. So we're just going to follow this path down to the S. And then we need to look for P, but at this point, we actually don't have a P node under the S, so we need to add it. That's all we do. We just add another node and add a pointer from S to P. And similarly, P was just created, so it doesn't have any children, so we need to add that S down at the bottom. And then now we have this word asps in our try. And the insertion algorithm for tries is big O of n, where n is the length of the word. It doesn't have anything to do with the size of the try, which is particularly nice because generally, so if we're talking about words here, words are typically bounded by, maybe like 20 or 30 letters. So having to do some constant multiple of 20 to 30 letters in steps for an algorithm is very good. Obviously, tries can get very large, and once they get really big, you're going to end up using a lot of memory, but you're still going to be using less memory than you would be with something like a linked list or an array. So this is a pretty good data structure for representing sets of words. Next thing that we're going to do is just search. So search is going to look a lot like insert, because with insertion, essentially what we're doing is we're following the path that we would expect the word to be at, and just creating nodes along the way if they don't exist. So for search, we're actually just going to do the same thing. We're going to follow the path. So we start at A, go down to S, and finally we go to K, and we find that there is a K node, and there's no children under it, which means that it's the end. It's the end of a word, I should say. And so we found it. Again, this is a big O of n operation where n is the length of the word once again. We're only doing 3 comparisons in this case for a word of length 3. So if this happened to not be here, we would end up actually short-circuiting at some point, because if we went to A and then to S and say that S didn't have a pointer to K, then we know that the word isn't there. We know exactly where the word would be in the try if it did exist. So if it doesn't exist, we can short-circuit. Deletion is slightly more complicated, but you can probably just figure out the algorithm yourself if you kind of stare long enough at it. So here we're going to delete the word apt. So we follow this path here down to apt. We've got that word in there. So again, we're going to do something very similar, and we're going to basically search for the word. So following the same algorithm as before, start with A, go down to P, go down to T. We found T, and what we do next is we don't want to delete all of these nodes, because some of them are required in the try to represent other words. For example, if we deleted P, then we would break the link between the A and like the apple word, basically. The apple word would be gibberish at that point. So we only need to delete the nodes that aren't essential for other words to be represented in the data structure, which basically means go back up the try in the same way that you traverse downwards and delete any nodes without any children. So the first thing we're going to do is T doesn't have any children, so we're just going to delete that. And then we're going to backtrack. So we'll look back at the node that we looked at previously when we were searching, which is that P right there. But P actually has another child, this P here. So we don't want to delete it. And that's it. We've deleted the word. Apt is no longer represented in the try, but we haven't broken any other words in the process, which is exactly what we wanted to do. And again, this is a big O of n operation, where n is, again, the length of the word. This is actually pretty atypical. When you're talking about big O notation, usually that n is going to represent the size of whatever data structure you're looking at and how many elements are in it. The fact that this is operating on the length of the words or the sequences or whatever you're storing in the try is actually pretty nice. That's a very good runtime. So we're going to look at the application that we're going to look at today is auto-completion. So, you know, when you're typing on your iPhone and it tells you, hey, do you want to type where when you type WHE? etc. This is one way that you might do that in a simple way using a try. So the first thing we're going to do is add a bunch of more words. I only want to do this because it makes this slightly more interesting. Instead of looking at just a small try, let's look at a slightly larger one. And I also wanted to add some more words because I wanted to mention this case right here. So in the case where we have, for example, asked in the past, as well as the present tense form ask, just regular ask, we need some way to differentiate between the two. So we can add like these end of word indicators as like a node in the same way that we had a terminator in our singly linked lists, etc. So so we know that ask is in the data set because there's an end of word indicator, like it points to an end of word indicator. And that's all that means. I just wanted to point that out because it's a question that definitely could come up. If you have a word and then a longer word that has the same prefix, how do you store it? And this is how you do it. But okay, so let's search for something and try to get an autocomplete. The prefix that we're going to look at for now is APP. So imagine that you were typing in the search box and you typed APP into the search box, and the data set that you're working with for like previous searches is represented by this try here. So the first thing that we're going to do is we're going to traverse down the try, so APP, and we're going to look at this node and the subtry of it. So essentially what we're doing here is we're looking for words that start with APP and are stored in our try. So everything underneath here starts with APP, and we have a whole bunch of paths down to leaf nodes in the try. So what do we do? Like, if we have these three, we have three different paths down to a leaf, and that start with APP. So all we're going to do is just collect all those paths and use those as recommended search terms. So the first one, we just follow L and E and we get apple. We can follow LY and get apply, and we can follow LIED and get applied, which is cool. But imagine that you want to do this in real time, or as soon as somebody types a new letter, you want to update. We can do that. Essentially, tries make this really easy. So imagine that you typed 2 more letters after the APP. Instead of having to kind of redo all of this and start back at the beginning of the try, we can actually just traverse the try a couple more nodes down to that LI, and then we can look at the suggested search terms there. So that's what we're going to do. We're just going to look at LI after the APP and end up with this subtry, which is just one single path down to a leaf node, IED, and there we have it. We just collect the paths again, and we get one single path applied. And that's it. That's all there is to tries. They're extremely useful for this type of application. And if you find yourself needing to do simple autocomplete in one of your projects, I would recommend giving this a shot, playing around with it. It's fun. It's cool. Thank you for joining me, and I will see you next time.